Unit Operation Classroom. Today we are discussing thermometer transient response, temperature response. My name is Shekhar Bhattacharya. A thermometer initially at a steady state temperature of 30 degrees Celsius. So initially this is at 30 degrees Celsius. Let's say it is exposed to ambient environment, atmosphere. So initially its temperature is 30 degrees Celsius. That's what it is. It's steady state temperature 30 degrees Celsius. So this bulb is also exposed to 30 degrees Celsius and it is showing the reading of 30 degrees Celsius. Now, this is now inserted in a water bath at 90 degrees Celsius. So suddenly this is now inserted in a water bath here. So this water bath temperature is constant, uh, at 90 degrees Celsius. Okay. So at time t greater than equal to 0, this bulb is experiencing a temperature of 90 degrees Celsius. Okay, so it will start rising. So that's what we have to find out. The initial rate of temperature rise with the thermometer is 2 degrees Celsius second inverse. So basically, if you see the response of this thermometer here, so initially this is at 30 degrees Celsius. So that's what it is, 30 degrees Celsius. Okay. So when it is immersed in this 90 degrees Celsius constant temperature bar, so its temperature will start rising. So initially the driving force is very high. Now slowly the temperature of this bulb increases, so the driving force decreases. So slowly this will decrease and the temperature will asymptotically reach the bath temperature 90 degrees Celsius. Okay. So the initial, so at time t is equal to 0, the slope of this curve, that's what it says, initial rate of temperature rise, which is basically at time t is equal to 0, t dt over dt, right here, the time t is equal to, let's call 0 plus. Immediately after insertion, the slope is 2 degrees Celsius, second inverse. So this is my initial slope. And finally, of course, it will reach 90 degrees Celsius. So assuming first order behavior, we'll see what the first order behavior means. The thermometer reading in degrees Celsius after 1 minute, that means time is equal to 60 seconds, we have to find out. So first, let's see what is the thermometer follows first order behavior. What does that mean? Normally, for a first order behavior, we say the rate of change of the dependent variable. Here, what is the dependent variable? Temperature of the temperature reading of the thermometer. Okay. Temperature reading of the thermometer, that's a dependent variable. Of course, that is a function of time, is proportional. The rate of change of the dependent variable, which is this one, rate of change of the dependent variable with time now, is proportional to the driving force. What is the driving force? Which is the difference between the present value and the equilibrium value. So the equilibrium value is going to be T bar. That means finally it will reach in this 90 degrees Celsius. And at any time T, this is my temperature. So at any time T, the driving force is the difference between the bath temperature and the temperature at that particular point. Okay, so the rate of temperature rise at that particular point would be proportional to this driving force. That's basically the first order behavior. And the initial condition is that time t is equal to 0. Let's call this a 0 plus. That's dt over dt is 2 degrees Celsius and inverse. So temperature, of course, here is 30 degrees Celsius. Okay. So, right, when it is inserted here at time t is equal to 30 Celsius, just 0 plus, immediately after insertion or immersion in the temperature birth, this temperature we can assume to be 30 degrees Celsius, but the rate of temperature rise is 2 degrees Celsius, 7 inverse. Okay. So we can say this is equal to this one value here at time t is equal to 0 plus, and this value of k we have to find out. T bath temperature is 90 degrees Celsius and the temperature of the bulb is still 30 degrees Celsius. This is immediately after insertion. So k is equal to 1 by 30 second inverse. So we solve this first order equation. This is very easy. We do the integration here between the initial temperature 30 degrees Celsius at time t is equal to 0. And at any time t, let's assume this t is the temperature of the bulb, of the thermometer, shown in the thermometer. So this, of course, is there's a negative sign. So there will be a negative sign here. So this is T bar minus T divided by T minus 30. Okay, so that will be equal to KT. So T bar minus T. So this is basically very standard. So this is the final equation which expresses the temperature of the displayed on the thermometer as a function of time. And we already know what is value of K. So to find temperature at any time t 1 minute, that is 60 seconds. So this would be equal to 90. That's the t bar here. So this is 90 minus 30. And this, of course, is 60. T is equal to 60 seconds. And this we already found out 1 over 30 seconds. So this becomes 81.80 degrees Celsius. So the answer would be 81.9 degrees Celsius. Okay, that's the answer. Let's try to solve this problem in a slightly different way. We are solving this problem on an alternative solution using the transfer function concept. That's the first one, of course, is using the first order concept. Now we are using, of course, the transfer function of a first order system. We'll see how we can solve this one. Okay. So for that, let us define certain variables. TBT is the constant bath temperature experienced by the thermometer bulb, which is, of course, 90 degrees Celsius here. So this is the TBT. TBS is the initial steady state temperature experienced by the thermometer bulb. So initial steady state temperature, of course, is 30 degrees Celsius. So initial steady state temperature, that's 30 degrees Celsius. Okay. So the input variable in deviation form. So what is the input function here? Input function is 90 degree minus what's the difference in temperature. That's the driving force, right? So that's what we are showing. This XT is the input variable, which is 90 degree minus 30, that is 60 degrees Celsius. So then 60 UT. So if we take the Laplace transform of this one, this would be 60 over S. So this is basically a step function. Now let us call TMT is the temperature reading on the thermometer at any time t. After insertion at any time t, let's say this is one temperature or temperature displayed by the thermometer. TMS is the initial temperature reading of the thermometer, which is of course 30 degrees Celsius. That's t less than 0. So in the deviation form, this would be equal to TMT minus TMS. Okay, this was at any time t, and this was at steady state. That means time t less than 0. This is the output function in deviation form, and this, of course, is the Laplace transform. So we know in general for first order transfer function, this is equal to the standard form. Okay. Now for K, we know this gain is given as final change. This K is a final change in the thermometer reading. As you can say, this is my temperature, this is T. And this, of course, the way it is given. So the final change in the thermometer reading right here, okay, that would be, of course, 60 degrees Celsius minus 30. So how it is? So final change in thermometer reading would be initially at 30. That is finally, of course, at time t is good to infinity 90. So this would be equal to 60 degrees Celsius, right? And divided by the step change in bulb temperature. What, of course, is going to be the step change in bulb temperature? That means the input variable, that will be equal to 90 minus 30. So that is also again 60. So this value of K would be equal to 1. So the value of K is equal to 1. So this is equal to 1. So the transfer function in this case would be equal to 1 over tau s plus 1. So we can say Ys is equal to, so Xs, of course, is equal to 60 over S. We have seen, so this is equal to Ys equal to 60 over S, 1 by tau s plus 1. Now, we have to utilize, now we have to find out the value of tau. To find out the value of tau, we have to use the information which is given. The initial slope or the initial rate of temperature rise is 2 degrees Celsius inverted. Okay, this is a little tricky. Let's see. So we have to find out the initial rate of temperature rise. So this is, let's call this the temperature. Why is the temperature rise? So that is dy over dt temperature rise, why is the temperature, let's say 0 plus equal to, we can say dy minus ys. Ys is the steady state temperature, so this is constant, so this is nothing but equal to same as this one. So this would be equal, since this is equal to capital Y, we can say this is equal to dy over dt. So this initial rate of temperature rise, of course, is dy by over dt in terms of the deviation variable 0 plus. And these are 2 degree Celsius inverse. Now, let us use the concept of initial value theorem. We know that for a function, any function, the time at tending to 0, that means the initial value would be equal to, if we find out, if we take the Laplace transform of the transfer function, multiply that by s and make s tends to infinity, that will give me the functional value right at the initial time t is equal to 0. That's my initial value theorem. For us, of course, we have to find out the initial value. Of course, we have to find out the slope or the derivative of the function, not the function itself. Derivative of the function, that means rate of temperature rise. So that will be equal to temperature, rate of temperature rise. That's what we have to find out, not just the temperature. Okay, so this is not temperature. This is we have to find out the initial value of the slope, the rate of changing of temperature. Okay. Now, this, of course, we have seen this is 2 degrees Celsius given. So, if we can evaluate that, then, of course, we can find out the value of tau. Let's see how we can do that. How we can evaluate Fs. So, Fs, of course, is going to be equal to the Laplace transform, the derivative of the function. Laplace transform, the derivative of this function here. Okay, which is, of course, as we can say, Laplace transform derivative of function is given by this. We know that. Now here, y0, of course, is at any time at time z is equal to 0. We know this this deviation function is equal to 0 because it's equal to at time t is equal to 0. This was 30 degrees Celsius, and this was actually initial steady state temperature also 30 degrees Celsius, and this is at time t is equal to 0. At time t is equal to 0 plus it keeps on changing, but at time t is equal to 0, this is also 30, this is also 30. So this is equal to 0. So this is equal to 0. So this Fs is going to be equal to Sys. Okay. So going back to the initial value theorem, we can say the Laplace transform, the limit of that means at time t is equal to 0, that's the initial value of the derivative of the function or the temperature, rate of temperature rise. That's, of course, we say it's Fs. We know that Sfs is going to be S. This S is here, and Fs is equal to Sys. We have just seen it right here, Sys, right? So this should be equal to S tending to infinity, S square ys, S square, and we know ys is equal to this. We have seen that, so we substitute right here, and we can say this S cancels out, so we can say this is 60s divided by tau S plus 1. We divide by S, the numerator and the denominator. We can 60 by tau plus ys, and this tends to infinity. This will tend to 0, so this is going to be equal to 60 over tau. And this we know is 2 degrees Celsius per second. So tau is equal to 30 seconds. Just the way we have got it. Okay. So we can say ys is equal to 60 over s, tau s plus 1, where tau is equal to 30 seconds. Now, this is a very standard first order process. So this is 60 over tau. We take the tau out, 60 over tau. And of course, we take the s here. So this is equal to s plus 1 over tau right here. This is the standard. A is equal to 1 over 30. And these are very standard procedures. I'm not really going to this. And you know, the solution is yt is going to be equal to 60, 1 minus t minus 30, right? So yt, of course, is equal to T minus 30. So TMT, that is the temperature displayed by the thermometer at any time t, is going to equal 30 plus 60 into this function right here. Okay. So at time t is equal to 1 minute or 60 seconds, this is going to be equal to 81 points. So it is the same values what we have got initially by the first method. Okay, so what are the lessons learned from this problem? This problem is a temperature sensor dynamics problem, of course. The thermometers, thermocouples, RTDs, temperature transmitters, which are very extensively used in the chemical process industry, remember that do not show the actual process temperatures instantly, not immediately. They respond with a time lag, often first order. In fast heating, cooling operations, maybe heat exchanger, distillation columns, reactors carrying out strong exothermic reaction, this temperature lag must be considered carefully. Again, finally, the answer, of course, is here, be 81.9 degrees Celsius.